Okay, so given function f is two-dimensional case. Okay, given function f on a boundary, domain was a boundary on a closed bounded domain, right? So we want to find the absolute maximum value. So that's two possible possibilities here. So we assume that, okay, f attains the absolute maximum value at some point, okay, in D. Now this could be inside D, could be on the boundary, okay? So the case one, if this is in the interior of D, okay, then what happens? If it's inside, then you just needed to find the maximum value. Well, then this must be critical value, yeah, critical point. Then this is a critical point, okay? So critical point by definition is a differentiable or the derivative zero, okay? So that means if f is differentiable, then the derivative must be zero, okay? The second, or the second case is if this is on the boundary of D, okay? Then you cannot say derivatives, you know, this is right on the boundary, okay? But in either case, if you want to find absolute maximum value, what you have to do? You have to look at the value around the boundary and right, and trying to find this boundary. We call it partial D. Okay, this is D. This is the boundary. Okay, the boundary is denoted by partial D. Okay, that's a standard notation. So we have to find the maximum value of the function, okay, on the boundary. Because in order to find an absolute maximum value function on D, you have to, what they have to do is you have to find an absolute maximum value of f around the boundary and also the value at the critical point. Then you compare, okay? So because the function has you know, the function always, if it's continuous, yeah, it's always has an absolute maximum value somewhere. If it's inside the domain, then this is if it's inside domain, then this point must be critical point, okay, somewhere. If it's on the boundary, then you cannot talk about critical points, right? But in either case, okay, in either case, you have to look at the value on the boundary and to find the maximum, just like similar to the function with one variable. If you want to find the absolute maximum value of function defined on a closed interval, right? What do you have to do? You have to find the critical point inside the interval and find the value of the function at the critical point. Then also you have to look at the value of the function at the end point. Then you compare which one is larger, right? Because you only have two values at the two end points. So it's easy to see the maximum value, right? But maximum value, you know, which one is larger at the end point, right? But now our boundary is with the function has two variables and the boundary has is a one-dimensional curve, okay? That have a trouble here. But we, how do you find, yeah, how to find the maximum value of the function okay, along a curve, okay, in a domain, okay. So this is the function defined somewhere. Maybe could define the whole plane, okay. The function define the whole plane. So what we're going to do is we're trying to find this is a C, okay. The function defined everywhere else here. The function is defined here. So this is a D, okay. I want to find out the maximum value function along this curve. How to do that? Okay. The idea is very simple. Assuming the function differentiable, okay, I just give it. This curve is described by x, yeah, by x equals x of t, y equals y over t, okay, when t equals t naught, okay. So this curve can be determined by g, x, y, we assume that's curves, okay. And so because this is a curve along this this is parameterization, right? So you can get quickly, you differentiate, okay? You differentiate both sides, then what you get is you have a gradient of x of t, y over t, dot product, right? And the x prime t, y prime t, okay? That's gonna be 0. So in particular, at that particular point, if that point is x, yeah, x naught is gonna be x, right? Okay, at this particular point, you have okay. Then you have this is a perpendicular, right? The gradient of a g is in that direction. Okay. Now we assume the function has a absolute maximum value at that point. So we always have this, okay? For any t, for t close to t naught, okay? So when you differentiate, the derivative should be equal to 0, okay? So the derivative should be equal to 0, so that implies the gradient, the direction of the derivative, yeah. So when you differentiate with respect to t and set t to be 0, okay? So this is I should say, yeah, let me add one more step here. So the derivative of this function when t equal to t naught should be equal to 0, okay? Because this has a local maximum value when t equals t naught, okay? But when you differentiate this is going to be f, okay? And you also have this, okay? So that means you have two vectors perpendicular to the tangent vector. You have two vectors, right? This is tangent vector. You have a gradient of a g, right? And gradient f also perpendicular, maybe in that direction. So your conclusion is the gradient of f equals lambda of gradient. Okay, at that part. If the function has a yeah, so if f restricted to the curve C, okay, has a local extreme value, okay, okay, at the point on the curve C. Then you have this identity, okay? So it's proportional to each other, these two vectors. So this is the idea, okay? This is the idea. Now we conclude, we have the following theorem, okay? The following theorem doesn't matter, it's 2 variables, 3 variables. Here's the theorem. Okay. Okay. If F has a local maximum or minimum value at some point, okay, this should be subtracted to the constraint. Okay, the constraint is g of x, y equals k, okay? And we also assume that the gradient of g is not going to be 0, okay? Otherwise, we have trouble. Okay, then, first, we know that the gradient of this should be equal to, right? Second, we still use the condition. Okay, so you get 2 equations. I think you are able to find the point. Okay, 2 equations. Okay, and right, that's a necessary condition. Okay, this is necessary condition. Okay, now we don't say the function has a local maximum value in at some point in its domain. We only say it has a local maximum value along this curve determined by g equal to k. Okay, so that's why the gradient of f is not going to be 0. All right. Otherwise, if we remember, if the function local maximum value in the whole, for all the points nearby this, then the gradient of f is going to be 0. But if you only restrict it to the curve g equals k, then the gradient of f is not going to be 0. The gradient of f is going to be proportional to the gradient of g. Okay, that's a slightly different. So let's take a look at example. Let's take a look at example. Okay. So f of x is going to be 3x plus 1. Okay. Find the maximum value, and this is a typical example, and the minimum value of f restricted to the circle. Okay, x squared plus y squared equals 10. So that means I'm not talking about the function defined the whole plane. The function 3x plus y on the whole plane, it does not have a local maximum value. This, when we say as a maximum value, means absolute maximum value. Okay, so 3x plus y can be as large as possible or as small as possible. However, if it's restricted on the circle, okay, then the function becomes a function of one variable. Okay, it has the maximum value or the minimum value somewhere. So there's 2 different ways to solve this problem. Okay, there's 2 different ways to solve this problem. But the first method is very complicated. That's the first method. I just give you an idea how to do it. The first method, how do you find it? Okay, because the function is restricted to the circle. So you parameterize a circle, that's going to be square root 10 cosine t, y equals square root 10 sine t. T is between 0 and 2 pi, okay? So now the function restricted to, so you get a function of ht, okay? You restricted this, then it'll be 3 square root 10 cosine t plus square root 10 sine t. All you have to do is just find the maximum value of this function, okay? right? And this function is defined on this closed interval, okay? So you convert the problem in two-dimensional case to a problem in one-dimensional case. So you just need to find the maximum value for h of t and the minimum value for h of t. Now, to do this, we just, how to do that, right? We're back to the math 165, calculus 1, okay? So we differentiate, we get negative 3 square root 10 sine t plus square root 10 cosine t. And you set this to be 0, okay? Then you will get tangent t equals 1/3, okay? Now the trouble is you cannot find the value of t, okay? So it's not easy to solve. You have to find all the solutions. All the solutions, okay, this is a t, right? T, all the solutions, tangent t is positive. I think there's two angles here. One is T1, another one will be T2, okay? There'll be two solutions, okay? So T1 is arctangent 1/3. T2 is going to be pi plus arctangent 1/3, okay? Then you have a sine cosine. You know, I think it's easy to find the sine cosine, okay? Sine t cosine t. Why? Because you can use a triangle. Yeah, you can use this one. Tangent, this 1 and 3. So this is going to be square root 10, okay? So that's a T1. So as long as you find, and from here you can see that sine T1 is going to be 1 over square root t. Cosine T1 equals 3 over square root 10, okay? So you have two critical points for the function h over t. That is a function defined from 0 to pi. That's a T1, the T1, T2, T2 is T1 plus pi, okay? T2 is T1 plus pi, okay? So now we have to evaluate the function. So h of a T1, okay? H of a T1 is going to be, h is it's a square root 10, right? And we have a 3 cosine T1 plus sine T1, okay? 3 cosine T1 is going to be 3 square root 10. Sine T1 is going to be 1 over square root 10. So after compute it, it's going to be 10. Okay, then this is a value, right? H of a T2. I think H of T2, both sine and cosine would be negative. So I just simply write, yeah, because how to get it, right? It's T1, T2 just differ by pi. And here sine, cosine, they're all equal to, it's negative T1, okay? It's negative 10, right? That's a quick. All right, so since we already convert the function to restrict function to a strict line now, right? The circle becomes an interval right now, okay? So you also have to look at the value at the end point. The value at the end point is square root 10, 3 cosine 0, sine 0, so 3 square root 10. And h2 pi, it's the same, okay? That's going to be h0. It's a periodic function. So clearly, the maximum value is 10, and the minimum value is negative 10. Okay, so the maximum value of h, okay, which is maximum value of the function restricted to the circle, is going to be 10. The minimum value of h is going to be negative 10. Okay, so you get this answer using the knowledge from math 1, from calculus 1. Okay. Now, as you can see that, yes, we can solve the problem. We convert the problem, a function of 2 variables to a function of 1 variable. Okay, the idea is very simple. Let's go back to here, right? the function restricted on the circle. So circle is a one-dimensional object. It can parameterize by one parameter t, right, in this standard form. So when you restrict the function to the circle, you get a function for your variable. Then you just need to find maximum value or minimum value of this function in one variable, right? But still take time, you know. It's not easy to go through all the steps. Okay. But now we use our method. Okay, that's the second method, and you will see that that second method is much more powerful. Okay, and doesn't need a sine cosine. Okay, so we first of all, the circle is a level curve. Okay, so g of xy is going to be x squared plus y squared. Okay, so all I need is find the gradient of f. Okay, this is going to be just a constant vector. The gradient of g will be a little bit different, 2x and 2y, right? Right. If the function attains a local maximum value or local minimum value at some point, then at that point, the gradient of f is going to be lambda gradient of g. Okay, this is a point on the circle. So you have a x, y, not arbitrary. Okay, so let's put the details here. So you get 3, 1 equals lambda, 2x, 2y, and x squared plus y squared equals 10. Can we find x and y? I think we can. How many questions do we have here? We actually have 3 equations, 3 unknowns. Lambda, x, y. Why have 3 equations? Because the first equation is actually 2 equations here. Okay, so you can lambda definitely is not going to be 0 clearly, right? Otherwise, it's right hand side 0. So x, 2x lambda, right, is going to be, you know, compare, right? 3 equals 2 lambda. 1 equals 2 lambda y, right? This above equation, vector equation. So you will get x equals 3 over 2 lambda, y equals 1 over 2 lambda. Okay. Now we can put into the second equation, x squared plus y squared. So you get x squared plus y squared, 3 over 2 lambda squared, 1 over 2 lambda squared. This should be equal to 10. Okay, what do we get? The numerator is going to be 10. The denominator 2 lambda square equals 10, right? Okay, so then the 2 lambda square equals 1, 2 lambda equals plus minus 1. So lambda equals plus minus 1/2. So we not only determine the lambda, we also determine the xy in this case. X equals plus minus 3, y equals plus minus 1. Okay, when x is plus 3, y minus 3. So you should get 2 solutions. The reason you get 2 solutions is because around this circle, the function has a maximum value somewhere, has a minimum value somewhere, right? So you get 2 solutions, 2 points. You cannot have a maximum value, minimum value at the same point, then this will be a constant function. All right, so you get 2 solutions. You have 2 points. Then you look at the value of the function at those 2 points. So f 3, 1, right? The function is, you know, remember f of x, y is going to be 3x plus y, right? So 3 times 3 plus 1 equals 10. F negative 3, negative 1 is 3, negative 1, negative 3, negative 1, right? It's negative 10. So this is the maximum value. You just needed to look at these 2 values because Yeah, the function, you see the curve is closed curve, okay? The function, if the function has a local maximum value somewhere on the circle, and that point, okay, must be a solution of this, one of the solutions here, okay? And then if the function has a local minimum value somewhere on the circle, then that point also is a solution, one of the solutions. Okay, so you have two solutions here, right? 2 points. So now you get, you compare those two values, and the one must be maximum value, one is minimum. So I think it's, algebraically, it's much simpler when you solve the algebra equation. Okay. Okay. Now we can for a high dimensional case, like a three. Let's see. I'm going to maybe do one more example, then we look at the three-dimension case, function within three variables. Okay. All right, let's try problem 6, number 6. Okay, the function is going to be x times e to the y, and the restriction is, and this is still on the circle. Okay, it's still on the circle. Now, so this is on the circle, and this is my g of x, y. Okay, the function itself defined on the whole plane. Okay, defined everywhere, but we only restrict the circle. Okay, so this is a g equals 2. Okay, so around this circle. If the function has a maximum value somewhere here, then the around the circle, so then it's perpendicular to the tangent vector, okay, the gradient. Okay, the gradient at that particular point must be perpendicular to this tangent plane, but to this tangent line, right? But now, because this is a curve determined g of x, so g of x may be, I don't know, maybe in the same direction. Yeah, okay, in the same direction. So they must proportional to each other. Okay, if this is a point at which the function has a local maximum value. Okay, okay, this is the idea, right? Okay. All we have to do is just find the gradient of the function and the g f and the gradient of function g. So when you differentiate with respect to x, you get e to the y. When you differentiate with respect to y, you get the same function. The gradient of a g is still 2x, 2y. Okay. So if the function has a local maximum value, minimum value somewhere here, then you get two equations. Okay, the reason why they're proportional, I just explained to you. Okay, first of all, gradient f is always perpendicular to the tangent vector t. But if the function has a local maximum value or minimum value at that point along the circle, the gradient of f also must be perpendicular to t. So they're both perpendicular to t, and that forces those two vectors are proportional to each other in the same direction or opposite direction. Okay, so this is a g of x, y is still 2. So the details will be e to the y, x e to the negative y. So x times e to the y is going to be lambda 2x 2y, okay? And then x squared plus y squared equals 2. So you first of all, you have to solve for, yeah, the above equation is breaking into two equations. Yeah, So the vector equation actually has, give you two equations. E to the y equals lambda 2 lambda x, x e to the y equals 2 lambda y, okay? Then you have another equation, x squared plus y squared. So can we solve for x and y here? Can we solve for the x and y here? Okay. So that's this mixture, right? And let's see, we have trouble with the y variable. Okay, we have trouble with the y variable. Okay, x equals, let's try and, yeah, let's double check the computation. X times e to the y equals 2 lambda y. Okay. So you can, let's try this. Replace e to the y, okay, the second equation, right? E to the y is 2 lambda x, right? E to the y 2 lambda x equals 2 lambda y, and a surprise. So 2 canceled out, lambda is also canceled out. Lambda cannot be 0, okay? So lambda is also canceled out, okay? What we got here is x squared equals y. Okay. X squared equals y. So once you get an x, then you are able to get a y, right? So x squared is going to be y, and I'm not sure we're able to solve this. Okay, let's see. Did I copy the wrong one? Let me double check. Yes, it's correct. All right, so we tried to solve for x in terms of yeah, sometimes it's not easy to solve. It's a solve for x in terms of lambda, solve for y in terms of lambda, okay? So y is going to be, actually now you only have two equations, okay? So this is a 2 lambda x squared and 2 lambda y, so 2 lambda cancelled out, you get xy. So you only have basically you only have two equations, right? E to the y, right? Since I think we cannot get this, we cannot get the x easily. Okay, the reason is you see y equals x, right? Then how can we express x in terms of lambda? So y, you can put y here. So e to the x equals 2 lambda x. Okay, and yes, we do have a solution for x. The x will be expressed in terms of a lambda. It depends on lambda value. Okay. Okay, so we cannot look at this problem. We cannot solve for x and y. Okay, we cannot express x in terms of lambda in elementary form. Okay, so you can also replace x by yes. So question x should be equal to something depends on lambda, right? And yes, this equation has a solution. Now, so now that means not easy to use this method to find the absolute maximum, find the maximum value and minimum value, okay? So the question is how do you solve it, right? So you stop here. Now you have to go back to the first method in order to solve the problem, okay? In order to solve the problem. So the first method, Okay, so it's not working here, right? You cannot express x and y, then you determine the lambda value, okay? And then once you determine the lambda value, you still have to determine the x, y. So it's not I don't think it's not easy, okay? So you let x to be square root 2 cosine t, y equals square root 2 sine t, okay? And because this is on the circle, then the function restrict to the circle is going to be f, right? X over t, y over t, okay? So it's going to be square root 2 cosine t because x times e to the y, okay? So this is a function, periodic function. I'm not sure we are able to solve this problem. I just tell you, this is the wrong problem. We pick it up, but not every problem is solvable, right? So t is it's pure. This is a pure function. So you have to find the derivative, right? When you find the derivative, it's going to be negative square root 2 sine t e to the square root 2 sine t, right? And the plus square root 2 cosine t, and differential this is okay, then you differentiate this as square root 2 cosine t, and that should be 0, okay? Maybe this time it works, okay? So we have, you see, we can cancel this, right? When you set this equation, we also cancel square root 2. So negative sine t plus square root 2 cosine t squared equals 0, okay? As long as you find the value for cosine t, then you solve the problem. Now, I think we can solve this problem using the first method. So, okay, how to convert this cosine t to sine t, right? It's going to be negative sine t plus square root 2, 1 plus sine minus sine square root 2, right? So I will get negative square root 2 sine square root t minus sine t plus square root 2 equals 0. But yeah, I can change the sign. Okay. Use a quadratic formula. Okay, use a quadratic formula. Sine t is going to be 2 square root 2 here, minus b, plus minus b squared minus 4ac. Okay. Okay. So you will get negative 1 plus minus it's actually 9, right? So you're going to get negative 1 plus minus 3 to square root 2. So there are two possible solutions. When you choose a positive sign, minus 1 plus 3, I will get 2 over 3, right? Okay, I get the square root 2 over 2. Good. Another solution is when sine t equals negative 1 minus 3. I don't think you're going to get, so you will get negative 2 over square root 2 is negative square root 2, which is no solution because this is a bigger than less than negative 1. Okay, so you only have one solution. That's good. Okay, so sine t equals square root 2 over 2. So the first solution, sine t is going to be t1 is going to be what? Is going to be pi over 4, right? And the t2 is going to be for sine. You see, you only have two solutions, right? Both are positive. That's t1, that's t2. t2 is going to be pi minus pi over 3 pi over 4. So you have two solutions, great. Then you find the maximum value for h of t, okay? Yeah, you choose which one is large, okay? So h of t1, so it's a square root 2. I remember it's cosine, right? Cosine pi over 4, e to the square root 2 sine pi over 4. So this is going to be square root 2 over 2, e to the square root 2, square root 2 over 2. Now, after you simplify it, this just equal to e, okay? Another one is h of 2. So that this time it's going to be 3 pi over 4 e to the square root 2 sine 3 pi over 4. This will be negative, okay? Actually, it's negative e, okay? After you simplify it. Okay. Now, this is a local, actually is a maximum value, not necessarily local because this is only, okay? This is a maximum value. This will be the minimum value, okay? Okay, you have to use the classical, in some problems, you have to use the classical method, okay? You convert the function to a function of one variable, then you find the maximum value, minimum value. Now, I forgot to mention at the end of points, right? At the end of points, let's double check that because this function right now is defined on the interval, okay? So it's square root 2 cosine 0 e to the square root 2 sine 0. Sine 0 is going to be 0, so it's a square root 2. I think a square root 2 is smaller than e, okay? So don't worry about that. Okay, it's going to be also square root 2, okay? It's a periodic function. So this is a number between negative and positive. But so it's not always, you can use the method today to solve the problem. So that's why I show you two different methods. In this particular case, for this particular problem, I cannot. If you can solve this equation, tell me, okay? E to the x squared equals 2 lambda x. I cannot express x in terms of lambda. Then you determine the lambda. It's not easy, okay? You can, what you can do, try this is maybe, I don't think so. You can easily find out x and y, okay? Okay. All right, so now for function for 3 variables, we have a similar theory, okay? Its idea is the same, okay? So let me state the thing, okay? So how do we find the maximum minimum value for a function on the surface, okay? So if, here's the point. If f attains a local maximum or minimum value at a point, okay? And this function is subject to okay, then you have two equations. One is a gradient of f equals lambda of the gradient of this. Okay. Okay, this I have to assume that this is not going to be 0. We assume that, otherwise it's not true. Okay. It's a very similar statement. The proof is similar. I'm not going to talk about this. Okay. Now, let's take a look at a problem in 3 variables. Three variables. Okay, we have a good example. Okay, let's look at this example. This is a story problem. Okay, I want to discuss this in the class. A rectangular box. Okay, a rectangular box. Okay, without a lid is to be made from 12 square meters cardboard. Find the maximum value of such a box. Okay. Right. So basically, we know the rectangle box. We know the surface area. Okay. We just want to find out the maximum value of the maximum volume you can make. Okay. So the surface area is fixed. Okay. Find the maximum volume. Okay. Find the maximum value. I think the maximum value will be the volume of the cube, but we cannot tell right now. We can prove that. Okay. So how do you solve this problem? Well, this is the application, right? And you have three variables, x, y, z. So the volume is just x times y times z. Okay. But the surface area is twice of x, y, twice of y, z, twice of zx. Okay. You have a total 6 faces there. And you calculate the top one, bottom one have the same volume. That's our 2xy. The left and right, 2 faces and 2yz. And the front and back side, 2xz. Okay, this is going to be 12. So this is a typical problem, right? We have a volume function. We have the volume function. We have the restriction, right? 12. So you fix that. Okay. So how do we solve this problem? Yeah, the box does without the top, right? Okay, let me check. Yes. So now, yeah, we modified it. You're right. So remove this, but yeah, without it. Yeah, otherwise it's probably a bit easier. Now we have to solve this problem. Okay, just x, y. Okay. All right, so we have to find the gradient of f of v. Okay, v is a function. Okay, so the gradient of v is going to be yz and xz and xy, right? Differentiate the differential function with respect to each variable. The gradient of a, when the differential with respect to x, I get a y plus 2z. When the differential with respect to y, I get an x plus 2z, right? When the differential with respect to z, I get 2y and 2x. I think so. Yeah. Okay. Yes. So we have to find the points such that the function, yeah, here you see, here we know that x, y, z are all positive, right? That's all we have. Okay. So A equals 12. This surface is harder to draw. Okay, it's a surface. Okay, it's harder to draw it. It's unbounded surface, honestly. Okay, nearby, yeah, it's harder to draw the surface. Okay, this is a XYZ must be positive. So this is a picture. I think it's harder to draw it. It looks like that. Okay. Nearby the x-axis, y-axis, z-axis is, it goes to infinity. Okay. I'm not going to draw the picture. This is a equals 12. Okay. The function is restricted on this surface. If the function has a maximum value somewhere, okay, then that point, okay, the gradient of v must be equal to lambda for gradient of a, and a is going to be 12. So you have a how many questions you're going to get? Okay, you're going to get yz, xz, xy equals lambda, y plus 2z, x plus 2z, and the 2y plus 2x. Okay, another one is you still have this, x, a equals 12, so xy plus 2yz plus 2zx equals 12. Wow. So you have many equations. Let me write down here. Yz equals lambda, y plus 2z, and xz equals lambda x plus 2z, and xy equals lambda 2y plus 2x. Okay. Now, it's not easy to solve this, honestly, to solve this equation. You have several equations here, okay? You have several equations here, okay. Right? So lambda cannot be 0, okay? Lambda cannot be 0. Now, you have to, yeah, this is an algebraic question. So how do we solve it? X, Y, Y, Z, and blah, blah, you can plug YZ, XZ and XY into the above formula, okay? Then you get lambda, and all those numbers together, okay? So first of all, you see that lambda cannot be 0. You know why? Why it's not 0? Because if you put all the terms here, okay, and this goes to here, and this goes to here, and this goes to here, what you get is lambda, right, 2y plus 2x, and then you have a 2yz, so 2y plus 4z, and then you have 2xz, 2x plus 4z equals 12. And then lambda times something equals 12, and then lambda cannot be 0. Otherwise, you have a problem here, right? So you have a 4y, how many x? 2x, 2x, you have a 4x. Then you have a 4y, right? And have a 8z. Yeah, 8z. I'm surprised you have 8z, okay? So you can, do we have xy, 2x, 2y, 2x, and the 2yz, so 2y, 4z, and the 2zx, 2x, 4z. So you have an 8z and just 4y and just 4x. Okay, so that implies lambda is not going to be 0. Okay. Okay. You can also directly to see that if lambda is 0, yz should be 0, xz also should be 0, and xy should be 0. So then this is a, yeah. Okay. So now what is the next step? Well, you cannot use this equation to get, we're trying to express x, y, z in terms of lambda, right? So the trick here is you multiply each equation by x, the first equation. This equation I can multiply by x, right? And then xy plus 2xz, and then I multiply this equation by y, the second equation, then xy 2zy, then I multiply this equation by z, I get lambda 2yz and then 2xz. Equation 1, equation 2, equation 3. Okay, what you can get from here, okay, what you can see from here, okay. So the last two equations, the first, equation 2 and the equation 1. Let's take equation 2 and the equation 1. Equation 2 and the equation 1, this 2, right, should be equal, right? No, that's easy, right? So xy plus by equation 1 and the equation 2. 2xz should be equal xy plus 2zy. Then, okay, then xy cancelled out. Okay, so you get xz equals zy. Right? And similarly, equation 2 and the equation 3. By equation 2 and equation 3, right? You have xy plus 2zy should be equal to 2yz plus 2xz. So 2yz also canceled out. So you get xy equals 2xz. All right. Now we come to the point how they are simplifying those equations. Okay. Well, the first equation, you have to assume that these not, you have to say these is not going to be 0. So if z is 0, the volume is going to be 0, right? So we already assume that z, x, y, z are positive. Okay, x, y, z are positive. So z is not going to be 0. That implies x equals y. Okay, and here this implies x is cancelled out, y equals 2z. Okay, right? Yeah, the volume is going to be x times y, z. X, y, z cannot be 0. That's why you can cancel z. Okay, now you have a y equals, you can y equal, x equals y equals 2z. Okay. Then from here, I think you can what we can do, right? You have the values of x, y, z, and you can determine the x, y. Okay, you can determine the x, y because g, right? X, y is the restriction A. Let's go back to A, right? A is going to be the last equation, x, y, y, z to zx, right? So A xy, 2yz, 2xz, right? Remember this, right? This should be equal to, yeah, 2yz. This should be equal to 12. So let's use any of this it's going to be 12. So you can determine the x, determine the y, because all those numbers are same, right? You can let's just assume z is a parameter. Okay, so x times y is 2z, so x times y is 2z squared, right? X times both x times, right? This is x, right? Yeah. And then plus 2y, y is a 2z, right? And then z plus 2x, x is going to be 2z and z. So that's going to be 12, right? So you have 4, 4, 4. So 3/4, right? That's 12. So you get 12z squared equals 12. So z squared equals 1. Okay? Z squared equals 1 because we already assumed that z is positive, so z is going to be 1. If z is 1, then x is going to be 2z, so it's 2. Y is going to be 2. Okay? So I did not even mention the lambda here. Okay? You can determine the lambda, but there's no need to find the lambda. Okay? So if the function has, okay, if the volume has a maximum value at some point, okay, right? And here x positive, y positive, z positive, because all the edges. Then x equals 2, y equals 2, z equals 1. Z equals 1. And you can multiply this out. So volume is x times y z, 2 times 2 times 1. Okay, so x is 4. Okay, so this is going to be 4. Okay. Do you see, I just said, but the question is, does the function really have a maximum value here? This is just a maximum value or minimum value, right? It's necessary condition, does not mean guarantee. The function maybe has a value, the volume must be can be larger than that, could be go to infinity. And the reality, I don't think so. If the surface area is fixed, I think the volume is not going to be infinity. Otherwise, you can make in a huge box, right? So it's impossible. So we don't need to go further, to verify it further. Okay. So if the function has a maximum value, I just say a local maximum value, and this must be the absolute maximum value of the function. Okay. Yeah, this must be absolute value, absolute maximum value, because it's common sense, right? If you have a rectangular box, and if its a surface area is fixed, right? You cannot make it as the volume as large as you want. Okay, it must have a maximum value somewhere, right? Somewhere, and for some choice of x, y, z, right? Was x, y, z positive? So then you only find the one point. Okay, you only find the one critical point. So then the function must have a absolute maximum value at this point. There's no other choice. Okay. As you can see that it's pretty tricky, to find to solve the equations. It's not easy. So it requires you have a very good algebra skill to solve these equations. You get how many equations you're going to get? You get 4 equations. And for this particular problem, I don't need to find lambda. Okay, I still can solve the problem. Okay, there's no need to find the lambda. Okay. But our next, do I have a time? No, I don't have much time left. Let's just do one more example if possible. Okay. This three variables. It's the three variable problems. Well, they're all complicated here. Okay. Let's look at problem 12. Okay. Let me quickly finish that. Okay. X to the fourth, y to the fourth, z to the fourth, and then subject to x squared plus y squared plus z squared equals 1. So this is a function. It's a positive function on the sphere, okay? And so all I have to do is to find if the function has the maximum value somewhere, right? And that function must have minimum value somewhere here. So we want to find those 2 points, and then you have to look at the gradient. So this is going to be 4x cubed, 4y cubed, 4z cubed. And the gradient of g is going to be 2x, 2y, 2z, okay? So you're going to get, so the gradient of f should be equal to lambda gradient of g. And then I should have 3 equations. 4x cubed equals 2 lambda x, 4y cubed equals 2 lambda y, right? 4z cubed equals 2 lambda z. And I also have x squared plus y squared plus z squared equals 1. Okay. Now, to solve this equation, right? First of all, you have to say whether x can be 0 or not, right? If x can be 0, what happens to the y variable, right? So for the first equation implies either x equals 0, right? Or if x is not going to be 0, x squared, okay, equals half of lambda, okay, right? And similarly, it's y0, otherwise y squared equals half of lambda. Or you can get z equals 0, or z squared equals half of lambda. So there are total, how many possibilities there? 2 times 2, 8 possibility. It's 8 possibility, honestly. So it's not a, well, one case must be excluded. X squared plus y squared equals z squared should be 1. So you cannot say x equals 0, y equals 0, z equals 0. Right? So there's a possibility. Yeah. For example, when x equals 0, y equals 0, right? Then z squared equals lambda, right? So lambda is going to be, lambda is going to be z squared, put it into the equation. So 0 squared plus 0 squared plus z squared equals 1. So 1/2 lambda equals 1. So the implies lambda equals 2. Okay. Lambda equals 2, right? Then at this point, z is going to be, z squared is going to be 1. So z is going to be plus minus 1. Okay. So you have to look at all those points. So their points similarly can get all the other points plus minus 1, 0, 0, 0 plus minus 1, 0, right? And 0, 0 plus minus 1. You have to look at those points. Those are all the solutions. Okay. In that case, lambda is going to be 2. Okay. Now there's another case is only one of them is 0. Okay. Only one of them is 0. X is 0, but the y is not going to be 0. Okay. And z is not going to be 0. That's also possible. Okay. When x equals 0, y is not 0, y is going to be half of the lambda, right? Z is going to be half of lambda. Okay, so then you squared. Oh, wait a minute. So above, yeah, z square equals. Yeah, this I should. Yeah, this square is it's going to be, yeah, z is going to be half. No. Yeah, oh, this already z square here. Okay. So this is square. Okay. So when you add them together, you get lambda equals 1. Okay. So lambda equals 1, then y square equals 1, z square equals 1, right? No, 1/2. So you have a y equals plus or minus square 1/2, z equals plus minus 1 square 1/2. Yeah, you got too many solutions here. Okay, you got lots of points all over this sphere. Those are called the critical points. Okay, so this is going to be 0 plus okay, all those 4 points, and similarly, you can switch the order. 0 could be in the middle. Okay, it's a very similar, by symmetry. And the last one is no one of them is 0. X squared equals 1/2, right? Y squared equals 1/2 lambda. Z squared equals 1/2 lambda. In that case, okay, add them together, 3/2 lambda equals 1. Okay, so half of lambda equals 1/3. Okay, so that means x squared equals 1/3 because add them together, right? Yeah, and that is y squared, that is a z squared. So you also have a bunch of points, x equals plus minus square 1, y equals plus minus 1/3, z equals plus minus square 1/3. And then you have 8 points, okay? But the value will be different, okay? Well, it doesn't matter the sign. So I just put here, you have 8 points. You are going to get 8 points, okay? Then you check the value of the function at all the points. You find the maximum value. So on the sphere, there are a bunch of points here, here, and then there are lots of points on the surface, there or there. So, but they only find it many. Then you just look at the value of the function. You look at the value of the function at those points and find the maximum value. Okay. So at any of the points in this form, you get the same value. Okay. You get the same value. So the function at those points, the value of the function at those points, and plus minus square 1/3, plus minus square root 1/3 is going to be square 1/3 to the 4th power, and I have 3 terms here. Okay, so you just need to look at this one, and then for the top one here, you look at the value. Okay, you get twice of. Okay, you compare which one is large. Okay, and the very top one, I think the value is going to be 0. 0 plus minus 1 is just only 1. So which one is large? Which one is small? And among all those 3 values, you compare which one is large. 1, twice of this, and 3. Okay, which one is large? Okay, and the maximum value, I think I'm going to compute this. It's twice square. I think square is just 1/2, so it's 4. So this is 1/2, and this one 3, and I think it's going to be 9, it's 1/3. Okay, so clearly this is the minimum value. This will be the maximum value. Okay. Yeah, we cannot discuss too many problems. It's too complicated. We stop here.